Welcome back. Before we begin, if you're listening tonight, feel free to share in the comments what you're curious about lately. A part of the universe you'd like to learn with, or simply rest with. Tonight, we're exploring calm, black hole science. Black holes are often described in dramatic ways, but at their core, they are among the simplest physical objects in the universe. They are not holes in space. They are not regions of constant destruction. They are not actively pulling everything inward. A black hole is a concentration of mass. More precisely, it is a region where a large amount of mass has been compressed into a very small volume, creating an extremely strong gravitational field nearby. Gravity depends on two things: mass and distance. When mass is spread out, gravity is gentle. When the same mass is compressed into a smaller region, gravity becomes much stronger close by. That is the defining feature of a black hole. Nothing about this requires motion or urgency. The black hole itself is not doing anything dramatic. The events that create black holes can be energetic, but once formation is complete, the object settles into a quiet, stable state. A black hole does not roam through space searching for matter. It does not grow rapidly on its own. It does not pull from afar any more strongly than other objects of the same mass. From a distance, a black hole behaves exactly like any other object with equivalent mass. If a star were replaced by a black hole of the same mass, the surrounding objects would continue moving along their existing paths. Orbits would remain unchanged. This is because gravity at a distance depends only on mass, not on brightness, composition, or appearance. The difference between a black hole and an ordinary object becomes important only at very close distances. Near a black hole, space itself becomes strongly curved. Paths that would normally allow escape begin to bend inward. At a certain boundary, called the event horizon, escape is no longer possible. The event horizon is not a surface. It is not solid. It is not a physical wall. It is a location in space defined by motion. At that distance, the speed required to escape exceeds the speed of light. Beyond this boundary, all possible paths lead inward. Nothing special happens at the event horizon itself. There is no sudden force or shock. An object crossing it would not experience an immediate change. From the outside, the event horizon marks a limit on what can be observed. From the inside, physics continues smoothly. Most of the universe exists far from black holes. Stars are separated by vast distances. Black holes are even more widely spaced. Because of this, black holes rarely interact with their surroundings. They spend most of their existence unchanged, quiet, stable. From a physics perspective, black holes are remarkably simple. They can be fully described using only a few properties: their mass, their rotation, and, in theory, their electric charge. In practice, most black holes have almost no charge. Their behavior is governed almost entirely by mass and spin. This simplicity means that black holes do not evolve quickly. Once formed, they settle into a steady state. They persist across timescales far longer than the lifetimes of stars. Even the slow processes that eventually reduce their mass operate over spans of time so long that they are effectively constant. In this sense, black holes are patient objects. They change slowly. They interact rarely. They exist primarily as regions where gravity is strong, not as active agents. The space around a black hole is not chaotic. It is structured. Gravity curves space in a smooth, predictable way. Objects passing nearby follow curved paths. Some pass by and continue on. Some enter stable orbits. Only those that approach very closely are captured. Most matter never comes close enough for that to happen. The calm nature of black holes is often obscured by language. Words like consume or devour suggest urgency and motion. In reality, black holes wait. They do not reach outward. They respond only to what arrives. From a distance, they are quiet participants in the universe. They follow the same physical rules as everything else. Mass shapes gravity. Gravity shapes motion. Motion unfolds over time. In that sense, black holes are not exceptions to physics. They are extreme examples of it. And like most large-scale physical systems, they are defined not by sudden change, but by long-term stability. Black holes do not appear suddenly. They are the outcome of long processes that unfold quietly over time. To understand how black holes form, it helps to begin with ordinary stars. A star is a balance. Gravity pulls inward, trying to compress the star. Energy produced in the star's core pushes outward, resisting collapse. As long as these two influences remain balanced, the star remains stable. This balance can last for millions or even billions of years. Inside a star, nuclear reactions convert lighter elements into heavier ones. This process releases energy. That energy moves outward through the star and eventually escapes as light and heat. The outward flow of energy is what counteracts gravity. As long as fuel is available, the balance holds. Over time, fuel is gradually consumed. The rate depends on the mass of the star. Small stars burn fuel slowly. Large stars burn fuel more quickly. Eventually, the core of a star changes. Lighter elements become depleted. Heavier elements accumulate. These heavier elements do not release energy in the same way. As energy production slows, the outward pressure weakens. Gravity does not weaken. When the balance shifts, the star begins to change. For many stars, this change leads to gentle outcomes. The star may expand, shed outer layers, and leave behind a dense remnant. In some cases, the core becomes a white dwarf. In others, a neutron star. These remnants are compact and stable. They represent matter in tightly packed configurations. Only the most massive stars continue further. In very massive stars, gravity becomes overwhelming once nuclear fuel is exhausted. The core contracts rapidly. This contraction is not chaotic. It is driven by gravity, acting without sufficient opposition. As the core collapses, density increases dramatically. Particles are forced closer together. At first, new forms of pressure resist collapse. Electrons are compressed. Then protons and electrons combine to form neutrons. This process creates a neutron-rich core. In many cases, neutron pressure halts the collapse. The result is a neutron star. But if the core is massive enough, even this pressure is insufficient. Gravity continues to compress matter beyond known stable states. At this point, the core collapses past the point where escape is possible. A black hole forms. This formation occurs deep within the star. From the outside, the process may be accompanied by a supernova, a release of energy as the star's outer layers are expelled. But the black hole itself forms quietly. Once the collapse passes a certain threshold, the outcome is sealed. the event horizon forms. From that moment onward, the black hole exists as a stable object. The violent stages end. What remains is not an explosion, but a remnant. The newly formed black hole does not continue collapsing in the usual sense. The collapse that created it is complete. From the outside, the black hole is defined by its mass, its rotation, and its gravitational influence. Time passes, the black hole settles. Surrounding material may orbit for a while, slowly drifting inward or outward. If material falls in, the black hole's mass increases slightly. If nothing approaches, nothing happens. In many cases, black holes are born alone. The surrounding region becomes quiet. No further dramatic events occur. The black hole simply persists. This persistence is one of the most important aspects of black hole physics. Black holes are long-lived. They do not burn fuel. They do not radiate light in the usual way. They do not require energy input to maintain their structure. They exist as stable solutions to the equations of gravity. Once formed, they can last far longer than the stars that created them. Some black holes are only a few times more massive than the Sun. Others grow much larger. Over time, black holes can merge with other black holes. These mergers occur when two black holes orbit one another closely. As they orbit, they emit gravitational waves. This emission carries energy away, causing the orbit to shrink. Eventually, the two black holes merge. The merger itself is brief on cosmic timescales. Afterward, the resulting black hole settles into a new stable state. Again, the outcome is not ongoing activity. It is a new equilibrium. Larger black holes form at the centers of galaxies. Their origins are still being studied, but they likely grow gradually. They begin as smaller black holes. Over time, they accumulate mass through mergers and in falling material. This growth occurs slowly. The surrounding galaxy evolves around them. Even the largest black holes do not dominate their galaxies in an active way. They influence motion through gravity, not through constant interaction. Most of the time, they remain quiet. From a distance, a black hole's formation is a single event. From the perspective of deep time, it is just one step in a long sequence. Matter cycles through different states. Stars form. Stars evolve. Remnants persist. Black holes represent one of the most stable endpoints of this process. They are not transitional objects. They are long-term features of the universe. The universe contains many black holes, but they occupy very little volume. Most of space is empty. Most matter never approaches a black hole. Because of this, black holes do not dominate cosmic behavior. They participate quietly. They exist within the larger structure. Their formation reflects the universe's tendency toward stable outcomes. When mass becomes dense enough and energy production ends, gravity determines the result. That result is not chaos. It is a new, persistent configuration. From stellar collapse to long-lived remnant, the process follows a clear pattern. Balance holds until it cannot. Gravity completes its work. A stable object remains. The universe does not rush this process. It allows stars to live full lifetimes. It allows collapse only when conditions require it. And once collapse concludes, it allows the remnant to endure. In this way, black holes are not signs of destruction. They are signs of completion. They mark the end of one phase and the beginning of a long, quiet persistence that can last for timescales far beyond ordinary experience. That persistence is what defines black holes most clearly. Not what they consume, but how long they remain. Once a black hole has formed, most of what defines it happens not at its center, but in the space around it. This surrounding region is governed by gravity in a very precise way. From a distance, the gravitational influence of a black hole is ordinary. It decreases smoothly with distance. Objects far away respond gently. As one moves closer, gravity becomes stronger, but it does so gradually. There is no sudden boundary where behavior changes abruptly. Space around a black hole remains structured. Paths remain predictable. Objects approaching a black hole follow curved trajectories, determined by their speed and direction. Some pass by and continue outward. Some enter long, stable orbits. Only a small fraction approach closely enough to cross the event horizon. Most matter never reaches that point. Orbits around black holes are governed by the same principles that shape planetary systems. Inertia carries objects forward. Gravity curves their paths. The difference lies in scale. Near a black hole, the curvature of space becomes more pronounced. Paths bend more strongly. Yet even here, motion remains smooth. There is no turbulence inherent to gravity itself. An object in orbit around a black hole experiences steady acceleration, not chaos. If the object's path is stable, it can orbit for extremely long periods. Some stars orbit black holes for millions of years. Their paths are measured, predictable, and repeating. From a physics perspective, these orbits provide some of the clearest evidence of black holes' existence. By observing how stars move, scientists can infer the mass and position of an unseen object. The star's calm motion reveals the black hole's quiet presence. Closer to the black hole, orbital behavior changes. There is a minimum distance at which stable circular orbits can exist. Beyond this point, paths become less stable. Still, instability does not mean immediate collapse. Objects may follow elongated or spiraling paths for long durations before crossing the event horizon. This spiraling is slow. It unfolds over many orbits. Each pass releases a small amount of energy, often through radiation if material is present. This radiation does not come from the black hole itself. It comes from matter interacting with matter. Gas clouds orbiting a black hole may compress and heat as they move. This heating produces light. The black hole remains dark. The light reveals motion, not consumption. In many systems, the region around a black hole is nearly empty. There is no bright disk. There is no constant activity. The black hole simply exists, shaping motion quietly. Space, near a black hole, behaves differently in subtle ways. Time passes more slowly, closer to the mass. Clocks would tick at different rates, depending on distance. This effect is smooth and continuous. There is no sudden change. As an object moves closer, the passage of time adjusts gradually. From the object's perspective, nothing unusual happens. From far away, the object appears to slow. This difference in time is a property of gravity itself. It reflects how mass shapes the structure of space and time together. Despite these effects, the experience of motion remains calm. There is no vibration, no sudden force. Physics continues uninterrupted. Even near the event horizon, paths are well defined. Equations still apply. From a mathematical perspective, the region around a black hole is one of the most orderly environments in the universe. The simplicity of black holes allows their surroundings to be described precisely. Few variables are needed. This precision contributes to stability. Nothing fluctuates randomly. Everything follows from mass, distance, and motion. Because of this, black holes are often used as reference points in physics. They provide clean systems where fundamental principles can be studied without interference. Their quiet nature makes them useful. They do not complicate the universe. They clarify it. From far away, a black hole's influence blends into the surrounding galaxy. Stars orbit as they would around any other massive object. The presence of the black hole does not disrupt the galaxy's structure. Only near the center does its influence dominate. Even there, motion remains ordered. This calm continuity is one of the most important aspects of black hole physics. It shows that even extreme gravity does not create chaos by default. Chaos arises from interactions between many objects, not from gravity alone. A black hole, isolated, is simple. It curves space. It shapes time. It allows motion to continue. Nothing about this process requires urgency. Nothing demands attention. From particles to stars, from orbits to galaxies, the same rules apply. Black holes fit into the universe without disruption. They are part of its long-term structure. They do not interrupt motion. They guide it, and in that guidance, they remain quiet, persistent features of a universe that favors smooth change over sudden transformation. When discussing what lies inside a black hole, it is important to move carefully, not because the subject is dangerous or unsettling, but because physics places clear limits on what can be known. The event horizon marks a boundary of information. It is not a physical surface, and it is not a location where matter suddenly changes character. It is a boundary defined by motion and communication. Once something crosses the event horizon, signals from it can no longer reach the outside universe. Light emitted inward cannot escape. Information becomes inaccessible, not destroyed. From the outside, this creates a natural limit. Physics does not stop working at the event horizon. Observation does. This distinction matters. The laws that govern matter, motion, and gravity continue smoothly across the boundary. There is no known physical process that activates specifically at the horizon. An object crossing it would not encounter a wall, a shock, or a sudden force. The transition is quiet. From the perspective of that object, space and time continue to behave locally as expected. The difference lies in the global structure of paths. Inside the event horizon, all possible paths lead inward. This is not because of attraction in the usual sense. It is because of geometry. The structure of space and time is arranged so that moving forward in time also means moving deeper into the black hole. There is no direction that leads outward. This does not imply acceleration or struggle. It is simply the shape of allowed motion. Physics describes this region using the same equations as outside, but with different boundary conditions. These equations remain well-defined until extremely small scales are reached. What happens at the very center of a black hole, often referred to as the singularity, is where current theories reach their limits. A singularity is not a place in the ordinary sense. It is a signal that a mathematical description has become incomplete. It indicates that densities and curvatures have reached values beyond what existing models can handle. This does not mean that physics breaks. It means that our descriptions are incomplete. Many physical theories have limits. They describe nature accurately within certain ranges and require refinement at extremes. The singularity represents one of those extremes. What can be said calmly and confidently is this: the region inside a black hole is not chaotic. It is highly constrained. Motion is directed. Paths are limited. There is no randomness introduced by gravity itself. Matter follows trajectories dictated by geometry. Time continues to progress locally. The passage of time does not halt. Processes do not freeze. They unfold according to the same local rules, even if their outcomes cannot be communicated outward. From the outside, the interior of a black hole appears timeless. Objects seem to slow as they approach the horizon. Signals stretch and fade. This is an effect of gravity on time, as seen from afar. It is not what the object itself experiences. From the object's perspective, crossing the horizon happens within a finite amount of time. Nothing dramatic marks the moment. Inside, the object continues along its path. Physics remains consistent locally. This consistency is a key theme. Black holes do not introduce new laws. They apply existing ones under extreme conditions. The calmness of this fact is often overlooked. There is no sudden transition from order to disorder. There is only a gradual narrowing of possible futures. Inside the event horizon, the future is constrained. Outside options disappear. Inside, motion continues along the remaining paths. This is a geometric inevitability, not an act of force. Because information cannot escape, the interior becomes isolated. It does not influence the outside universe beyond its mass, spin, and charge. This isolation contributes to the long-term stability of black holes. They do not leak complexity outward. They do not transmit chaos. They remain simple from the outside, regardless of internal detail. This simplicity is sometimes described as black holes having no hair. All the details of what fell in become inaccessible. What remains observable is limited and stable. From a cosmic perspective, this is efficient. Complexity is absorbed without spreading. The universe remains orderly. The interior of a black hole is not a place of ongoing destruction. It is a region where motion and time are constrained by geometry. Processes complete their paths. Outcomes occur, but they do so without affecting the broader structure of the universe. This containment is part of what allows black holes to exist without disrupting their surroundings. They isolate extreme conditions. They prevent those conditions from propagating. In that sense, black holes contribute to cosmic calm. They allow gravity to reach its most intense expressions without destabilizing larger systems. The universe does not become more chaotic because black holes exist. It becomes more stable. Extreme outcomes are contained. Information boundaries prevent complexity from spreading uncontrollably. This role is subtle but important. When viewed this way, black holes are not threats to cosmic order. They are part of how order is maintained. They mark the limits of communication, not the breakdown of physics. Inside the event horizon, physics continues quietly. It does not announce itself. It does not escalate. It follows the same principles that govern the rest of the universe, simply applied under conditions where paths are tightly constrained. This is what physics allows us to say calmly. Not that the interior is unknowable in a dramatic sense, but that it is inaccessible by design. The universe permits such regions. It contains them, and in doing so, it preserves the smooth, predictable behavior of everything else. Black holes do not exist apart from their environments. Once formed, they become part of larger systems, moving and evolving along with everything around them. Most black holes are embedded within galaxies. They orbit the galactic center just like stars do, following paths shaped by the combined gravitational field of the galaxy. Their presence does not disrupt this motion. A black hole carries mass, but it does not introduce instability simply by existing. In fact, black holes often occupy regions where mass is already concentrated. This is especially true for the largest black holes found at the centers of galaxies. At the heart of most large galaxies lies a supermassive black hole. These objects can be millions or billions of times more massive than the Sun. Despite their size, they occupy a region of space that is remarkably small. Their gravitational influence becomes dominant only very close to the center. Farther out, the combined mass of stars, gas, and dark matter shapes motion more strongly. Stars orbit the galactic center on long, curved paths. Their motion reflects the overall structure of the galaxy, not the presence of a single object. Even near the center, stars can orbit calmly for millions of years. Their paths are predictable. The black hole does not pull them inward suddenly. It does not act like a drain. It simply contributes to the gravitational landscape. In many galaxies, the central black hole is inactive. It is not surrounded by bright disks or energetic emissions. It exists quietly. Matter passes by without interaction. The galaxy evolves around it. When matter does approach a black hole closely, it does so because of local conditions. Gas clouds may drift inward over long periods. Stars may pass nearby due to orbital changes. These events are rare and unfold slowly. They do not define the black hole's everyday existence. The relationship between galaxies and their central black holes appears to be balanced. Observations show that the mass of a central black hole is often related to the mass of the galaxy's central region. This suggests a shared history. As galaxies grow and merge, their black holes grow as well. This growth occurs gradually. Mergers between galaxies bring black holes together. Over time, these black holes orbit one another, lose energy, and merge. The result is a new black hole that settles into the combined system. Afterward, the galaxy continues its evolution. The black hole does not dominate. It integrates. At smaller scales, black holes formed from individual stars also exist within galaxies. These stellar mass black holes move through the galaxy as ordinary objects. They orbit the center. They pass near stars without interaction. They remain unseen unless they interact with nearby matter. Most of the time, they remain isolated. This isolation is important. It means black holes do not frequently influence their surroundings. They are part of the background structure. Their presence contributes to the total mass of the galaxy, but not to its immediate activity. From a physics perspective, black holes act as stable anchors within galactic systems. They store mass in compact form. They participate in gravitational interactions without generating turbulence. Their simplicity contributes to long-term stability. The galaxy does not need to compensate for their existence. It adjusts naturally. Over deep time, black holes and galaxies co-evolve. Their growth slows as available matter becomes diffuse. Star formation declines. Mergers become less frequent. The system settles. At this stage, black holes persist as long-lived features. They do not require maintenance. They do not decay quickly. They remain as part of the galactic structure for billions of years. This endurance is one of their defining characteristics. In the context of a galaxy, a black hole is not an anomaly. It is an endpoint. Matter that once participated in dynamic processes has reached a stable configuration. The galaxy carries this configuration forward. Motion continues around it. Paths remain smooth. Nothing about the presence of a black hole forces rapid change. The larger the scale, the less disruptive the influence. At galactic scales, gravity averages out. The black hole becomes one contributor among many. Its role is subtle. It shapes motion locally, but it does not dictate global behavior. This subtlety is why galaxies can host black holes without appearing unstable. They are not dominated by them. They coexist. From a distance, a galaxy with a black hole looks no different than a galaxy without visible activity. The calm motion of stars reveals no urgency. The black hole remains quiet. In this way, black holes fit naturally into the universe. They do not interrupt its rhythms. They become part of the long-term structure that persists across cosmic time. From formation to integration, their story is one of quiet inclusion. They begin as remnants of collapse. They end as stable components of galaxies. And in between, they spend most of their existence doing very little at all. That stillness is not absence. It is balance. And balance, at cosmic scales, is what allows systems to endure. One of the most subtle influences of a black hole is its effect on time. This effect is not unique to black holes. It arises from gravity itself. Where mass exists, time passes differently. In regions of stronger gravity, time moves more slowly, relative to regions of weaker gravity. This relationship is smooth and continuous. There is no threshold where time suddenly changes behavior. Near Earth, the effect is small. Clocks on satellites tick slightly faster than clocks on the surface. Near a black hole, the effect becomes more pronounced. As an object approaches a black hole, the passage of time for that object slows relative to distant observers. This slowing is gradual. There is no moment when time stops. Instead, each step closer corresponds to a small adjustment. From far away, an object approaching the event horizon appears to move more slowly. Signals take longer to arrive. Light stretches. Eventually, signals fade. This fading does not mean the object halts. It means communication becomes increasingly delayed. From the object's own perspective, time continues normally. Clocks tick, processes unfold. There is no sensation of slowing. This difference between perspectives is a natural consequence of how gravity shapes space-time. Time is not separate from space. They are aspects of a single structure. Mass bends this structure. Motion follows its shape. Near a black hole, the bending becomes extreme, but it remains orderly. Time does not behave erratically. It behaves predictably, according to geometry. This predictability allows physicists to describe black holes precisely. Even under extreme conditions, equations remain consistent. The calmness of this behavior is important. It shows that gravity does not introduce randomness. It introduces curvature. Time near a black hole is not distorted in an unpredictable way. It is stretched smoothly. This stretching has practical consequences. Processes near a black hole appear slowed to distant observers. Orbits take longer to complete. Signals take longer to propagate. Yet nothing feels unusual locally. This consistency is a hallmark of physical law. Even at the edge of what is observable, the universe behaves regularly. Black holes simply reveal this regularity more clearly. They provide environments where the relationship between gravity and time becomes noticeable. Despite popular descriptions, time does not freeze at the event horizon. From a distant viewpoint, signals become increasingly delayed, but the object itself continues. The idea of frozen time arises from observation limits, not from physical interruption. Inside the horizon, time still exists. It continues to progress locally. What changes is direction. Just as space becomes constrained, so does the future. Paths forward lead inward. This does not involve acceleration or force. It is a consequence of geometry. The flow of time near a black hole illustrates a broader truth. Time is not absolute. Its rate depends on context. Gravity provides that context. This dependence does not destabilize the universe. It allows different regions to coexist smoothly. Near massive objects, time slows. Far from mass, it passes more quickly. These differences do not conflict. They integrate. Across the universe, time flows at many rates simultaneously, yet causality remains intact. Events occur in order. Nothing violates consistency. Black holes demonstrate that even extreme differences in time flow can exist without disruption. They localize extreme conditions. They prevent them from spreading. This containment contributes to long-term stability. From a cosmic perspective, the influence of black holes on time is limited. Their effects dominate only nearby. Beyond that, time resumes its familiar pace. Galaxies evolve. Stars orbit. Clusters drift. The presence of black holes does not alter the overall progression. It adds texture, not turbulence. The flow of time around black holes also unfolds over deep time. The processes associated with them are slow. Accretion occurs gradually. Mergers unfold over long spans. Even the slow loss of mass predicted by quantum effects operates on timescales far beyond ordinary experience. Black holes persist while time continues around them. They are not interruptions in the timeline. They are features within it. Time accommodates them. It bends around them. It continues past them. This accommodation is smooth. It does not require correction. The universe does not struggle to integrate black holes into its temporal structure. It does so naturally. From the smallest clocks to the longest eras, time remains coherent. Black holes remind us that time's behavior depends on where we are, not on what we expect. They reveal that time can slow without stopping, that it can stretch without tearing, that it can vary without chaos. This revelation is not unsettling. It is stabilizing. It shows that even under extreme conditions, the universe remains orderly. Physics continues. Patterns hold. The flow of time adjusts, but it does not break. In the presence of black holes, time remains one of the universe's most reliable features. It moves forward. It carries systems through change, and it does so calmly, even where gravity is strongest. Black holes are often thought of as solitary objects, but over deep time, some encounter one another. These encounters do not begin suddenly. They begin as distant relationships. Two black holes may form in the same region of a galaxy, or be brought together when galaxies merge. At first, the black holes are far apart. Each follows its own path through space, shaped by gravity and inertia. As they move through their environment, small interactions gradually change their motion. They lose energy in subtle ways. Their paths curve. Over long periods, they drift closer. This approach is not rapid. It unfolds over millions or billions of years. When two black holes come within range of one another, they begin to orbit. This orbit is calm and predictable. They circle a shared center of mass, much like stars in a binary system. The motion is smooth. There is no turbulence. The system settles into a stable configuration. As the black holes orbit, they emit gravitational waves. These waves are not disturbances in matter. They are ripples in space-time itself. They carry energy away from the system. The amount of energy lost at first is extremely small, so small that the orbit changes only slightly. Each orbit releases a little more energy. With time, the orbit tightens. The black holes move closer together. This process is gradual. For most of the system's lifetime, the change is barely noticeable. The black holes spend the vast majority of their time in this slow dance. Only near the end does the pace increase. Even then, the motion remains orderly. The laws of physics guide every step. As the black holes draw very close, the emission of gravitational waves becomes stronger. Space and time around them flex gently but precisely. These waves propagate outward at the speed of light. They pass through space without interacting strongly with matter. By the time they reach distant regions, they are extremely faint. Their presence can only be detected with sensitive instruments. The merger itself is brief. On cosmic timescales, it is nearly instantaneous. The two horizons join. A single black hole remains. Immediately after the merger, the new black hole is not perfectly smooth. It vibrates slightly. These vibrations are not chaotic. They follow well-defined patterns. As energy is released, the vibrations fade. The black hole settles into a stable form. This settling is called ringdown. It is the final stage of the merger. Once complete, the black hole behaves like any other. It has a mass. It has a spin. It follows the same gravitational rules. Nothing about the surrounding universe changes abruptly. The gravitational waves continue outward. They carry information about the merger. They spread across space, becoming weaker as they travel. Eventually, they blend into the background of the universe. They do not disrupt systems they pass through. They do not accumulate. They simply pass. This is an important point. Even the most energetic black hole mergers do not destabilize the universe. They release energy, but that energy is distributed across immense volumes of space. Its effect is gentle. From a distance, the universe remains calm. Black hole mergers illustrate how extreme events can be contained. They show that even when gravity operates at its strongest, the outcome is order, not chaos. Energy is released in a structured way. Motion remains guided. Systems settle. From a broader perspective, gravitational waves are part of the universe's quiet background. They are always present. Most originate from distant events long past. They pass unnoticed. They do not demand attention. Their existence does not change the rhythm of cosmic evolution. They simply carry information. Black holes merge rarely. Most black holes never encounter another. Those that do spend most of their time approaching slowly. The dramatic moment is brief. The aftermath is stable. This pattern reflects a broader truth about the universe. Change tends to occur in short episodes, separated by long periods of continuity. The continuity dominates. The episodes pass. From particles to planets, from stars to galaxies, the same behavior appears. Systems evolve through calm persistence. When interactions occur, they are absorbed. The universe does not amplify disturbance. It dissipates it. Black hole mergers are among the most extreme gravitational events known. Yet their effects are subtle when viewed across space and time. They do not fracture structure. They reinforce it. They allow mass and energy to rearrange into new stable configurations. Once the merger is complete, the universe continues. Stars orbit, galaxies rotate, clusters drift. The new black hole becomes part of the existing structure. It does not dominate, it integrates. This integration is key. It shows that even the most intense gravitational interactions fit within the universe's broader tendency toward balance. Nothing is wasted. Nothing is destabilized. Energy moves outward. Structure remains. In this way, black hole mergers are not disruptions. They are transitions, quiet transitions governed by the same laws that shape the rest of the cosmos. And once complete, the universe resumes its calm, steady unfolding. Beyond mergers and motion, black holes are defined by how they persist across deep time. They are among the longest-lasting objects in the universe. Once formed, a black hole requires no fuel. It does not burn. It does not cool in the usual way. Its structure is maintained entirely by gravity. Because of this, black holes change very slowly. On ordinary timescales, they are effectively permanent. There is, however, a subtle process that affects black holes over extremely long periods. This process is known as evaporation. It does not involve heat, flames, or radiation from the black hole itself. It arises from quantum effects near the event horizon. At very small scales, empty space is not completely empty. Particles and antiparticles briefly appear and disappear. Near the event horizon, these fluctuations can become unbalanced. Occasionally, one particle escapes while the other is absorbed. To a distant observer, this looks like the black hole has emitted a tiny amount of energy. This emission is extraordinarily weak. For stellar mass black holes, the effect is negligible. The time required for noticeable change is far longer than the current age of the universe. For supermassive black holes, the time scale is even longer. Trillions upon trillions of years would pass before evaporation becomes significant. This means that for almost all of cosmic history, black holes remain unchanged. They endure while stars are born and fade. They persist while galaxies evolve. They outlast nearly every other structure. This endurance gives black holes a unique role in the universe. They act as long-term repositories of mass. They preserve information about the universe's past, even if that information is inaccessible. They remain when more dynamic systems have quieted. Over deep time, as star formation declines and galaxies grow calmer, black holes become increasingly prominent simply because they remain. Their presence does not increase. everything else becomes less active. From a future perspective, black holes are not dominant because they act. They are dominant because they persist. This persistence aligns with the universe's broader trajectory. As energy spreads and processes slow, stable configurations become more common. Black holes represent one of the most stable configurations allowed by physics. They do not require balance between competing forces. They exist as endpoints. In the far future, when stars have faded and galaxies have settled, black holes continue to orbit quietly within clusters. Motion persists. Gravity continues. Time flows. The universe does not become empty. It becomes sparse. In that sparse environment, black holes remain as anchors of structure. They curve space gently. They influence motion subtly. They do not disturb. Eventually, over timescales, far beyond practical imagination, even black holes change. Evaporation proceeds. Mass decreases slowly. The process accelerates only at the very end. Even then, it unfolds quietly relative to the universe as a whole. The disappearance of a black hole does not send shock waves through space. It releases energy gently, spread across time and distance. By the time such events occur, the universe is vast and quiet. Their impact is minimal. From this perspective, black holes are not symbols of endings. They are symbols of duration. They show how the universe allows extreme conditions to exist without haste. They illustrate that persistence, not intensity, defines long-term behavior. Black holes teach a calm lesson about time. They remind us that the universe operates on scales where patience is built into the laws themselves. Processes unfold fully. Nothing is rushed. Even the most extreme objects change slowly. As the universe ages, black holes transition from dramatic ideas to quiet fixtures. They become part of the background. They participate in the universe's slow movement toward equilibrium. In that movement, they neither resist nor accelerate change. They simply remain until change arrives naturally. From formation to merger, from merger to endurance, from endurance to eventual fading, black holes trace a complete arc. That arc spans more time than most other phenomena. It is smooth. It is continuous. It is governed by the same gentle rules that shape everything else. In this way, black holes fit comfortably into the universe's long story. They are not interruptions. They are chapters, long chapters, written slowly. And like much of the universe, their story is defined not by urgency, but by patience, by continuity, by the calm unfolding of physics across time that has no immediate end. When black holes are placed back into the full context of the universe, their role becomes clearer. They are not central actors driving events everywhere. They are participants within a much larger system. The universe does not organize itself around black holes. Black holes organize themselves within the universe. Most regions of space are far removed from them. Between galaxies, space is thin and quiet. Between stars, distances are vast. Between black holes, distances are even greater. Because of this separation, black holes rarely influence one another directly. They exist as isolated features within a broadly calm environment. This isolation matters. It ensures that the extreme conditions associated with black holes do not propagate widely. They remain local. Gravity, even at its strongest, diminishes with distance. Beyond a certain range, a black hole's presence blends seamlessly into the background gravitational field. At those distances, motion is shaped by the combined mass of many objects. No single source dominates. This averaging effect is one of the reasons the universe remains stable. Extreme conditions are diluted by scale. Black holes also illustrate an important distinction between intensity and influence. Near a black hole, gravity can be extreme. Far from it, the same object behaves like any other mass. Its intensity does not translate into widespread disruption. This separation of scales allows the universe to host extreme phenomena without becoming chaotic. From a physical standpoint, this is efficient. It allows local specialization without global instability. Black holes occupy the extremes. Most of the universe operates in moderate conditions. These moderate conditions dominate cosmic behavior. They define the long-term evolution of structure. As the universe ages, activity continues to shift toward quieter modes. Star formation slows. Galactic interactions become less frequent. Large-scale structure stabilizes. Black holes remain present, but they do not become more active. They simply persist. Their stillness contrasts with the dynamism of earlier eras. This contrast highlights the universe's trajectory. It moves from rapid change toward slow continuation. Black holes fit naturally into this progression. They are stable endpoints that require little maintenance. They do not demand energy. They do not introduce complexity. They remain. From a philosophical perspective, black holes often symbolize mystery or finality. From a physical perspective, they symbolize restraint. They show how the universe limits extremes. They demonstrate that even the most concentrated mass can be contained. They reveal that the laws of physics are consistent across all scales. Nothing special needs to happen for the universe to accommodate them. The same principles that govern planets and stars govern black holes. Only the parameters differ. This consistency is one of the most calming aspects of physics. It means that no region of the universe is fundamentally alien. Even the most extreme objects follow familiar rules. They simply operate where those rules are applied strongly. Black holes also emphasize the importance of perspective. What appears dramatic at small scales becomes subtle at large ones. What seems intense nearby becomes negligible far away. The universe encourages distance. It spreads things out. It allows phenomena to exist without interference. This spreading contributes to calm. In a universe without scale, everything would interact strongly. In a universe with scale, most interactions are gentle. Black holes exist within that scaled structure. They are intense locally, but quiet globally. As time progresses, their relative importance changes. They outlast stars. They outlast many galactic features. Eventually, they become some of the last remaining compact objects. Even then, they do not dominate behavior. They coexist within a sparse environment. Motion continues. Expansion proceeds. Equilibrium deepens. The universe does not revolve around black holes. It accommodates them. They are examples of how extreme conditions can be integrated without disruption. They illustrate the universe's capacity for balance. They show that calm is not the absence of intensity, but the containment of it. From formation to deep time, black holes trace a story that aligns with the universe's broader behavior. They emerge when balance ends. They persist when activity fades. They change slowly. They integrate quietly. This quiet integration is their defining characteristic. They are not engines of chaos. They are markers of stability. In the end, black holes remind us that the universe favors endurance over urgency, that even the most extreme outcomes settle into long periods of stillness, that physics, when applied over vast scales, produces calm more often than conflict, and in that calm, the universe continues, structured, balanced, and patient, with black holes resting within it as steady, silent features of a system that changes slowly by design. As we step back one final time, black holes are best understood not as endings, but as limits. They represent boundaries within physics, places where familiar descriptions reach their maximum expression. Gravity does not fail at a black hole. It completes its work. What changes is not the law, but the range over which the law is applied. A black hole marks the point where mass has been concentrated as tightly as possible, without introducing instability into the wider universe. Beyond that point, nature does not escalate. It contains. This containment is essential. Without it, extreme conditions could propagate outward and destabilize larger systems. Instead, black holes localize extremes. They isolate them. The universe continues around them unaffected. From this perspective, black holes are not destructive objects. They are regulatory ones. They set boundaries on what gravity can do without disrupting everything else. They define where influence ends. This role becomes clearer when compared to other physical limits. Temperature has limits. Speed has limits. Density has limits. Black holes are the gravitational expression of those same principles. They are not exceptions. They are constraints. Once formed, they do not seek further change. They do not demand interaction. They exist within the universe's long-term architecture as fixed reference points. Their mass contributes to structure. Their presence shapes motion locally. Beyond that, they remain silent. This silence is important. It means that black holes do not accelerate the universe toward disorder. They do not trigger cascades. They do not amplify instability. They absorb it. Matter that reaches them is removed from further interaction. Energy that enters is contained. Complexity is simplified. The surrounding universe becomes calmer, not more active. This is one reason black holes fit so well into cosmic evolution. As the universe ages, systems tend toward lower activity. Processes slow, differences even out. Black holes align with this trend. They persist without agitation. They embody stillness within motion. At the largest scales, the universe favors such configurations. Stable structures last. Unstable ones fade. Black holes remain because they require no balance to maintain. They are self-contained outcomes. From a long-term view, this makes them predictable. They do not surprise. They do not change character. A black hole formed billions of years ago behaves the same today. Its surroundings may evolve. Its environment may shift. The black hole itself remains consistent. This consistency reinforces cosmic order. It provides anchors within the flow of time, points where behavior does not fluctuate. In a universe defined by motion and change, such anchors matter. They help ensure that change unfolds smoothly, that transitions do not cascade uncontrollably, that local extremes do not become global ones. Black holes demonstrate that even the most intense phenomena can be bounded. They show that the universe has built-in limits that preserve coherence. Nothing runs away. Nothing overwhelms. Everything fits within a larger pattern. As the universe continues toward equilibrium, black holes remain part of the landscape. They neither resist nor accelerate that movement. They coexist with expansion. They coexist with cooling. They coexist with the thinning of matter. Eventually, in the far future, even they fade. But until then, they serve as quiet markers of what gravity can achieve and where it stops, not as catastrophes, not as threats, but as stable conclusions. They show that physics does not escalate endlessly. It resolves, it settles, it contains, and once contained, it allows the universe to continue calmly, with structure intact and motion unbroken. In this way, black holes are not symbols of darkness. They are symbols of balance. They represent the universe's ability to accommodate extremes without losing harmony. They mark the edges of possibility while preserving the whole. And within that preserved whole, everything else continues. Planets orbiting, stars aging, galaxies drifting, unchanged by the quiet presence of these deep, stable limits. That is the final role of black holes in the calm structure of the universe. Not endings, but boundaries that allow everything else to go on. When black holes are viewed across the full scale of the universe, their meaning becomes simpler. They are not mysteries that disrupt understanding. They are confirmations of it. They show that the same physical principles apply everywhere, even where conditions are extreme. Gravity behaves consistently. Motion follows structure. Time adjusts smoothly. Nothing breaks. Black holes demonstrate that the universe does not rely on constant intervention to remain ordered. It relies on limits. Those limits are not barriers. They are boundaries that keep systems coherent. Extreme gravity does not spill outward. Extreme density does not propagate chaos. Instead, the universe contains these conditions quietly. This containment allows everything else to remain calm. Stars can orbit, galaxies can evolve, cosmic structure can persist. Black holes occupy very little space, yet they illustrate how restraint operates at the largest scales. They remind us that intensity does not imply instability, that concentration does not require disruption, that even the most compressed outcomes settle into long-term balance. Over deep time, black holes become part of the background architecture of the universe. They persist while other systems change. They remain while activity slows. They exist without urgency. From the earliest stages of cosmic history to the far future, black holes trace a steady line. They form when conditions require it. They integrate without disturbance. They endure without effort. And eventually, they fade without consequence. This arc mirrors the universe itself, a movement from activity to stability, from contrast to balance, from complexity toward simplicity. Nothing is forced. Nothing is rushed. Physics unfolds at its natural pace. Black holes are not exceptions to this process. They are expressions of it. They show that the universe can host extremes while remaining calm. That order does not depend on gentleness alone, but on structure. That even where gravity is strongest, behavior remains predictable. In that sense, black holes are not dark interruptions in the story of the universe. They are quiet confirmations that the story continues smoothly, governed by rules that never stop applying. And with that understanding, the universe becomes easier to rest within, large, ordered, patient. At this scale of the universe, there is little change. The regions between galaxies are defined less by what is present and more by what is absent. Intergalactic space contains only trace amounts of matter, a few hydrogen atoms, spread across enormous distances. Light travels here for millions of years without interruption. There are no solid boundaries, no edges, only expansion. Galaxies move apart, not because they are traveling through space, but because space itself is stretching. This expansion occurs everywhere, uniformly, without preference or direction. On these scales, time is measured differently. Processes unfold over spans far longer than human history. A galaxy completes a single rotation over hundreds of millions of years. Stars form, evolve, and disappear, while the larger structure remains largely unchanged. From this perspective, motion appears almost still. Between galaxy clusters, gravitational influence weakens. Matter becomes sparse. Interactions become rare. Particles travel vast distances without encountering anything at all. Even radiation, once emitted, continues outward indefinitely, unless acted upon by gravity. There is no background sound. Sound requires a medium. Intergalactic space provides none. What remains is silence, not as an absence, but as a physical condition. Light, however, persists. Photons released billions of years ago continue moving outward, their wavelengths slowly stretching as the universe expands. This stretching is measurable. It is known as redshift dash dash, a key observation that reveals the universe is growing larger over time. The farther a galaxy appears, the faster it is moving away, not due to velocity alone, but due to expansion itself. Across these distances, structure emerges quietly. Galaxies cluster along filaments of dark matter, forming vast cosmic webs. Between these filaments lie enormous voids, regions containing almost nothing. These voids are among the largest known structures in the observable universe. Some span hundreds of millions of light years. Within them, matter is so diffuse that even gravity has little effect. Dark matter plays a role here. Though invisible, its presence can be inferred through gravitational influence. It shapes the motion of galaxies and guides the formation of large-scale structure. Without dark matter, the universe would appear very different. Its effects are subtle, persistent, and continuous. Time continues forward, even where little else occurs. Atomic decay proceeds. Photons travel. Space expands. Nothing is static, even in regions that appear empty. Change simply happens on scales that are difficult to perceive. Far from stars, temperature approaches a limit. The background temperature of space hovers just above absolute zero dash dash. A remnant of the early universe, this cosmic microwave background fills all of space uniformly. It is the oldest light observable, dating back nearly 13.8 billion years. Even here, the universe carries memory. As expansion continues, distances increase. Galaxies beyond a certain point will eventually move out of observational range. Their light will never reach us, not because it disappears, But because space grows faster than light can cross it, this is not destruction, it is separation. On the largest scales, the universe trends toward simplicity, fewer interactions, lower energy states, greater uniformity. This gradual movement toward equilibrium is described by entropy. Entropy increases, not through disorder alone, but through probability. The most likely state is the one with the least constraint. Intergalactic space is an expression of that tendency. Wide, sparse, unforced, it does not resist observation, nor does it invite it. It simply exists, according to fundamental laws. From this vantage, the universe is not dramatic. It is patient, governed by constants, guided by expansion, shaped by gravity, acting over incomprehensible distances, and it continues, without urgency, without conclusion. Thanks for spending this time with us. If this exploration of deep space physics was helpful, you can support the channel by liking the video and subscribing for future long-form science journeys. New videos explore space, time, and the structure of the universe, with a focus on clarity, scale, and calm observation. If you have questions or topics you'd like explored in future episodes, feel free to share them in the comments. Until next time, thanks for being here.